All right, we're going to use this as a review for your upcoming quiz and hopefully go over the major topics that we've been doing the last few days. So to start it off, we want to take a look at just graphs in general. And by now we've seen several different graphs, but I want to just show you a couple examples of some graphs here and just sketch a couple lines on there. If you were to look at this graph here, and I asked you what it shows me about the object's motion. The misconception is that just a shape of a graph alone tells you anything about an object's motion. This shape does not mean anything until we start assigning axes to our graph. So now if I asked you that same question and you saw it as a position time graph, now this graph actually has a meaning. This shape, as we've seen before in the toy car lab and our other practice from last unit, this means a constant velocity. But if we were to switch up the axis and give a velocity time graph, that same shape now represents a different concept. So we have to be a lot more careful about what we have on our axis and understanding that this shape itself means something specific to that variable. So let's take a look at the graph down below. For this graph, again, this shape means nothing until I start assigning axes to this. What's on the y-axis, what's on the x-axis. I want you to start getting in a better habit of, before you just make a gut reaction about what you see and what motion this would mean, to first clearly understand what you're looking at on your graph. So if we make this a position time graph, and we think about what an object would have to do to make that position time graph, this would be an object just standing still over time. They're not moving, they're not moving, they're not moving, they're still at the same position over the entire time period. But if we switch this to a velocity time graph, now this same shape has totally different meaning, because when I'm graphing velocity now, I'm telling you how fast the object's going over the period of time. And this is something going at the same exact velocity for the entire rate. So the point of this is just to be more careful about when you see shapes on graphs, don't just assume you know that that shape means a certain motion. We need to make sure that we're looking at the variables on the axes first to then understand what shape we're seeing on the graph. All right, I next want to transition into our story so far and the graphs that we've seen. We started out in the toy car lab with a position time graph that showed constant velocity. And we know it's constant because the change in position divided by time is happening in a uniform way. We only have one slope throughout this graph, therefore there's only one velocity that that object is going. If we take a look at the units of that, to calculate slope, your slope would be equal to the change in the y-axis, which for us is position, divided by the change in the x-axis of time. Well, those units measured on that graph, we measure position in meters and we measure time in seconds. So that gave us this concept of velocity. That velocity in its standard unit is a meter divided by a second. So that we understood as a constant velocity when we saw that shape, and we worked with that and worked with the math models, and then we started a new type of motion with a ball or a wheel rolling down a hill. So with the wheel rolling down the hill, our graph came out like this. It was curved, and it was a quadratic graph. Again, that was still position and time. And what we noticed about that was that the slope value, try to draw a little tangent line on here for you. The slope value was changing the entire time. If we looked at the slope in the beginning, the slope of that line is 0, meaning the velocity was next to 0. But as I go around the graph, that slope gets steeper and steeper and steeper, indicating the velocity is getting faster and faster and faster over time. So this was not a constant velocity graph. This was a uniformly accelerating graph, and because of that we need a different math model and different equations to help describe that shape. So let's get into the equations on these graphs that we derived and talk about how we can use those in order to make predictions. There was two major graphs that we manipulated this original data of position and time, and we formed by going through some extra practice. One graph, especially important for what we're doing, is making a velocity time graph from the same set of data. And what we saw when we got a velocity time graph off of this curved xt graph is that it formed a linear function. And so thinking more about this, what does that actually mean about the velocity? Well, that means that your velocity value started at 0 down here, and then as time went on, say a time a little bit later, your velocity is larger. And that's happening in a uniform way. If you doubled the time, your velocity would double. And so as time moves on, your velocity increases in a uniform way. This is the concept of something accelerating. It's changing its velocity. In this case it was speeding up, but it could mean slowing down or changing direction. And this is the first major graph that we got. The second graph that we looked at was a linear version of our original graph to see if we could get any more information off of it. Because we can't write an equation of a curve, it's helpful to linearize a graph and make it in the form of y equals mx plus b as a straight line. So how do you linearize a quadratic graph? Well, you have to square all of your time values. And by doing that, that gave us a linear function with a straight line. Now we can start to make math models. For the linear graph, that got us an equation that said x equals 1/2 a t squared plus starting position. This was the formula that came off of this graph. For the vt graph, we got a function that said v final equals acceleration times time plus v initial. Again, two separate equations, both linear equations, coming from two different graphs. These two graphs, although they look similar, they do give you different values when you start analyzing the linear function. And to kind of show you what I mean by that, let's just take a look at this velocity time graph first. By doing the slope of that graph, I'd be taking the change in velocity divided by the change in time, or the change in meters per second divided by seconds, which can reduce down to meters per second squared, a value of acceleration. The slope of a VT graph is your true acceleration. So the slope of this graph is your actual acceleration for your object. When I go over to the xt graph, x versus t squared graph, the slope calculation would be a change in position over a change in time squared. Again, with the units on that, that would be meters over seconds squared. So you see, again, we have acceleration units here, we have acceleration units here. The only difference then is the amount of acceleration that this gives you. Technically, a x versus t squared graph only gives you 1/2 of your actual acceleration. So the slope on this graph is 1/2 of your accel, and that is a result that you're not graphing the same value. You're graphing velocities here, and you're graphing positions here. So, why do we need two graphs? Why do we need two separate equations? Well, sometimes you are more interested in your final velocity, and so you're going to be looking at how this velocity compares to time, looking at this function here, Vf equals at plus v naught. Other times, you're going to be interested in how far you ended up, like what was your final position. Well, in that case, you have this equation. So, depending on what you're looking for, whether it be final velocity or final position or maybe accelerations and times embedded within this, we use the appropriate equation out of our toolbox to help us get there. And that's why we need two separate equations for this type of motion.